This is a short session of the research short papers. We have 3 of them this afternoon, and what I'd like to do is to invite Shashi to bring the authors of the first paper, and the authors of the first paper are Goutham, Sekar, Bharani, Ujjaini, Kempaiah, Ruben, John, Mampilli, and Subramaniam, Kalambur. Performance sensitivity of operating system parameters in microservice environments. So who's coming up?
Goutham is on stage.
Welcome. So Goutham, you should know how to start off on the sharing the screen, and we'll be happy to go. We have 10 minutes for you now.
Yes, sir.
Which means that Q&A included, it will be 10.
Yeah. Am I audible and is the screen visible?
Yeah.
Yeah.
So maybe 6-7 minutes elevator pitch, and then we'll have a couple of questions.
Yeah, sure. So good evening. I'm Goutham Sekar from PS University, and I'm going to present the paper.
I have a request. Somebody's microphone is also on. I think there's an echo that's coming up. Goutham.
Yeah, there's some echo. I'm not sure who is.
Yeah. All right. Continue.
Yeah. So I'm going to present the paper, Performance Sensitivity of Operating System Parameters in Microservice Environments, which is co-authored by Bharani, Ujjaini, Kempaiah, Ruben, John, Mampilli, and Dr. Subramaniam, Kalambur. Yeah, so in the recent past, like if you consider the 5-6 years ago, applications were mainly focused on using a monolithic architecture where all its functionalities or services were under one big program. So currently, there's a shift towards a microservice environment in which it's composed of small autonomous servers. This kind of an architecture actually provides advantage in terms of increased modularity, smaller and faster to deploy, and are easy to scale. And hence, it's getting adopted quicker these days. So a microservice application usually it runs on Dockerized containers that heavily communicate amongst each other, and thus producing a large amounts of pressure on the operating system in terms of CPU or resource utilizations. So this paper is focused on trying to reduce this OS pressure and improving the performance of a microservice application in terms of the tail latency and average latency. And we have looked into different OS parameters that might be tuned for the better improvement of the microservice application. Moving on to the previous work. So the first one has investigated how the OS and network overheads impact the mid and tail latency of a microservice application. So they've looked into how the number of context switches and the interrupts are raised when a microservice application is at its maximum utilization. The second paper has attempted to characterize cache usage and its impact on performance when multiple workloads are co-located on a multi-core server. And the third one highlighted the importance of interference in operations performed by the host OS when there are a large number of containers that are communicating actively amongst them, which kind of introduces contention for resources and degrades the performance. So this paper has highlighted that point. But none of the papers have really tried to tune OS parameters or to improve the performance of a microservice application. So the parameters under consideration for this experiment are the disk write buffer size, the kernel thread affinity, and the TCP buffer size. So the disk write buffer size is governed by a variable called the dirty expire centiseconds, which what it means is basically the dirty data or the modified data in the page cache is written back into the disk after every t seconds. So by default, it takes the value of 30 seconds. So the disk to mitigate the input-output congestion, which is like a common bottleneck in microservice applications, we have tried to increase this particular value to improve the performance of the application. So moving on to kernel thread affinity. So kernel threads are important entities that handle the interrupts raised in a system. So to to improve the efficiency of handling these interrupts, we came up with two techniques, that is to which I'll be explaining later. And the TCP buffer size. So the common microservice applications introduce a lot of network overheads due to the heavy communication amongst them. So usually like the TCP buffer size is set at 128 kilobytes, which is small, and it's good enough for applications that do not handle these a lot of communication amongst them. So for this particular case, we try to increase the size of the TCP buffer so as to accommodate those like the data writes and data reads. And yeah, moving on to the experimental setup. So we have used two AMD servers. One is a 16-core processor with 64 GB of NUMA RAM. NUMA is basically non-uniform memory access, and a 24-core processor with 128 GB of NUMA RAM. So these were running on the Linux kernel version 4.15, and the operating system used is Ubuntu, which is Linux based, and it was the Ubuntu 18.04. And this is the architecture of the 16-core processor. So in this, each block actually represents a core complex, and each core complex has 4 cores in them. And if you look at the NUMA architecture, you have several nodes, and each node is assigned to a particular set of cores, and that's how the memory access happens there.
You should accelerate a little bit.
Yes, sir. Yeah.
Goutham.
Yeah. Yes, sir. Sure. Yeah. So this is the two test applications that we use are TStore and DeathStar. We have considered the browse profile, which is a read-intensive profile, and the buy profile, which is a write-intensive profile. And this is an open source application, which was done by the University of Würzburg in Germany. And this is the DeathStar application that contains 5 different services, and the one we've used is a social network microservice, which consists of 30 loosely coupled microservices that communicate amongst each other via Thrift RPC protocol. And we have actually used the compose post load profile, which is again a write intensive profile. And yeah, this is the dependency graph. And moving on to the describe. Yeah, so now the results, coming to the results section. So when we modify the dirty expire 70 seconds to 60 seconds, that is increase it from 30 to 60, we achieved about a 26% improvement in the average latency and a 99% improvement in the tail latency. And this was mainly due to the fact there was a reduction of 23% in the number of interrupts raised and a 22% reduction in the number of context switches. One more thing we validated was by decreasing the dirty expire 70 seconds to 15 seconds, the frequency of the disk writes increased, and hence the number of interrupts raised in context which is increased, which actually showed a degradation in performance, which can be seen when it's compared to the default case. And increasing the dirty expire 70 seconds to a value greater than 60 seconds might actually lead to data loss due to the power outages, since the data stored in that page cache is temporary. So the two techniques that were used for affinitizing kernel threads was the first one, which was affinitizing a kernel thread to a single core in each core complex.
One more minute.
Sir?
1 more minute. Continue.
Yes, sir. Yeah. A 22% improvement in the 99% tail latency, and affinitizing the kernel threads to a single core actually showed a sharp decline in system performance. The TCP buffer size was like calculated based on the link speed, and the product of the link speed and latency, and while increasing it from the default to 128 kilobytes to 256 kilobytes showed a 34% reduction in the number of context switches, and which was accompanied by a significant improvement in tail latency of up to 32%. But increasing it to a larger value, that is from 256 kilobytes to 512 kilobytes, actually put a strain on the memory of the host, which might be due to the fact that there might be memory overheads involved in allocating large blocks of
seconds
for TCP buffers. So the parameters that were considered previously were taken into consideration separately, and we combined them to form an optimal system configuration, which showed a 34% improvement in tail latency.
Okay. I think we're almost at the fag end, so
Yes. Yeah. Okay. The conclusion. To conclude, the tuning the OS parameters related to the frequency of disk writes, kernel thread affinity, and TCP buffer size brought about a reduction in the pressure that was applied on the operating system and also an improvement in the performance of both the test applications considered. And we believe this work lays the foundation for further research in identifying key OS parameters that might influence the performance of a system. Thank you. Now,
Wonderful, wonderful.
open to
questions. Any questions, please? So, are there no questions at all? I'm sure there must be a lot of people who must have at least one question. All right. So, if nobody has a question, then I have a question for Goutham Sekar.
Yes.
Quickly, I just wanted to know, you have designed this, what should I say, way of augmenting the microservice performance by choosing to play around with the operating system parameters.
Yes.
Right?
Sir. Yeah.
Now, and you have found a certain optimal level too, in terms of what happens if you increase it beyond the 16 seconds and what happens if it's below 30. Okay.
Yeah.
Now, this is for a certain kind of configuration and for a certain kind of workload. Doesn't this keep changing over a period of time with various other types of workloads and other types of usages of the server?
So for the experiment,
microservice, the pattern, the variety of workloads in the microservice environment is so very varied. So how does your thing stand? That's the question.
Yeah, so we tested it on two applications, that's tstore and Detsa, and both of them provide like different kinds of services which have read and write profiles. So we tested it on both of them and we compared the results, and the average was like we saw an improvement in performance with respect to tail latency and the average tail latency. And
Okay. All right. So on that note, we'd like to thank you, and we'll go to the next paper.
Yeah, thanks a lot.
Thank you very much. So a few claps for you.
Thanks a lot. So, yeah.
Yes, there it goes. A lot of claps and a thumbs up too. All right, Shashi, may I request you to bring in the next set of speakers?
Yes, sure.
The next paper is about real-time adaptable resource allocation for distributed data-intensive applications for cloud and edge environments by Jean-Didier Toto and Demosthenes Kyriasis from University of Piraeus, Greece. Are you all there?
Yes, I am connected. Can you hear me?
Yes.
I will share my screen now. Okay, I think you can all see my screen.
Right.
So
you have about 8-9 minutes to go, and I hope we have a quick Q&A as well. Please go ahead.
Okay. Okay. Thank you, sir. So the title of this research is a real-time adaptation resource allocation for distributed data-intensive application of a cloud and edge environments. The main goal is to allocate resource to a cloud application or the edge application that run on an environment where the workload is dynamic. So the approach developed in this paper is applicable on containerized and distributed applications, and our solution supports application composed of one or many components. So before going further, my name is Jean-Didier Toto Tom-Ata. I am Congolese, and I work as a research assistant at the University of Piraeus in Greece. We all know that cloud offers resources and services over the internet, and cloud application handle dynamic workload. And this application have resource requirements in order to ensure a good quality of service. And the workload and the resource allocated to an application are the main factor those application performance. But since the workload is not static, so there is a need to adjust dynamically a resource allocated to an application in order to keep stable the quality of service delivered. And some application running on the cloud, they have some constraints between components. And for instance, the bandwidth between the component A and the component B should not be inferior than some specific value, or the latency between the component C and B should not exceed some threshold. So how the deployment of all components can satisfy inter-component constraints and performance expected by the application owner. Some work were conducted to address challenges developed above. Stanskovsky proposed a distributed model using container technology. Rao proposed a distributed self-learning approach applied on virtual machine, and Islam approached the problematics by proposing an empirical prediction models. And some data-driven platform has been developed recently where a reinforcement learning is applied to discover the amount of resource needed. For example, I will say some few words about the project Melodic and Big Data Stack, where the adaptation is performed by a reinforcement learning algorithm, which train based on the real-time data. And those...
You need to accelerate a little bit.
Yes, and those platforms using adaptation based on the resource allocation only. So the adaptation proposed in this work is about the resource allocation and the application relocation, where the application can be moved from one node to another one, and the deployment pattern, which is the assignment or disassignment of component to a node. So the method followed in this paper start by the formulation of a constraint problem, where we have a set of nodes, candidates, and a set of components of the application that we want to deploy. So the output is obtained by filtering the universe of solution with component requirement and inter-component constraints. So the solution 1 and 2, for instance, will be selected based on their performance. And this performance is computed or predicted by the performance model, which is the second part of our methods. So given the application X that expose the response time as A and the latency as B, the latency from the user perspective, the application X is running on a node with some configuration. By configuration, we mean the properties that the cloud provider can modify. So for instance, we have the memory, the CPU, the number of instances, the average number of bounds, for example, in which is the average number of steps from the user to the node running the application. So since we want to reduce the response time and to reduce the latency, we can express the application performance as to express as follow. So the performance could be 1 divided by the response time times the latency.
Jean, you don't need to read the slide. You can give us a summary of it because you need to accelerate.
Okay. So sorry. So
we just need to skip. Don't worry about it.
Okay. So the strategy is about to correlate the metrics and the configurations. So in order to proceed to this correlation, a data set should be built, which contain different configurations. And from that, we can apply many techniques in order to discover the correlation.
Okay.
So for instance, if we apply a linear regression, we can end up with the expression, the two expression on the screen, where we have some coefficient assigned to each variable and we have some constant. So from A and B that we discover after having applied this technique, we can compute the performance and select the best deployment plan.
Okay.
So in order to experiment, we use some project, which is an open source project, and we added some functionalities of monitoring service discovery and capability of deployment on Docker Swarm. So this project is on GitHub and you can access it if you want. And we can then, from the orchestrator located in the cloud, deploy scale application on the edge node. And we are using Prometheus as a monitoring engine in order to collect metrics and to expose them to the orchestrator for analysis. We perform many experimentation. We try many algorithms, and we have 56% with linear regression, and we can reach 80% with decision tree, random forest, ADA boost regressor, gradient boosting regressor. So since the work is still ongoing, and we experiment with stacking regression, but now by adding a workload of the user as a configuration, and we can reach 83% of accuracy of predicting the performance of the application. So next we have to work on the prediction of the workload, if we can predict the workload in the future. And also we are working on improving the performance model accuracy. So this area of cloud and edge has many opportunity and future. So we aim to improve our techniques in order to deliver a very good adaptation of cloud and edge application.
Wonderful.
So that's it. Thank you.
Yeah.
Thank
Questions,
you very much.
please. Questions for John ZDA. All right. If there are no questions, I really appreciate your work. And since it's still work in progress, I would rather reserve the questions right now and get in touch with you later if I have. Okay. On that note, I'd like to give you a big round of applause and thank you so much. And I'd like to go on to the next paper, which is on the workload volatility management in data centers on the cloud by Priyanka and Sai Manohar from VMware and Nutanix. So are you all ready?
Yes, Priyanka is on stage.
Wonderful. Priyanka, you can start sharing your screen. You have about 7-8 minutes to go, and we'll have a couple of questions and we'll close off this session.
Sure. So are you guys able to see my screen?
Yeah.
Okay, great. So welcome to our talk on workload volatility management in data center and cloud for efficient resource management. To first start with the background on why we need to manage volatile workloads. We are no longer working with traditional applications like database and web servers. So the workloads now are evolving continuously. We now have many modern workloads like machine learning, big data, and container applications. These workloads are now more distributed across multiple VMs. Also, a diverse set of hardware like vGPUs are now supported. So all these changing features and requirements create many challenges for efficient resource management. And one of the challenges is workload volatility, which is our topic for today's talk. So why did we pick workload volatility? We all know that workloads are volatile to some extent in general. But with the introduction of these modern applications like containers, the workload volatility is prone to become more prominent now, and the need to manage such volatile workloads has grown. Since any resource management engine plays a crucial role in optimal utilization of available resources, Let's now see at how load balancers in the industry today work at higher level and how they manage these volatile workloads. The load balancers are designed to respond and react whenever there is a change in workload distribution. It reacts by recommending to move VMs from one host to a different host where more resources are available. Since the migration involves moving CPU and memory state of VMs, it has some cost associated in terms of resources needed on both source and destination nodes. So when we have a highly volatile data center, the workload distribution keeps varying continuously and the load balancer has to react continuously by recommending migrations. Having too many VM migrations has a huge impact on overall resource availability for the workloads and also on the performance of applications running inside the VM. To understand this further, let's look at an example. This chart here shows CPU utilization in a 4-node cluster that has highly volatile or continuously changing workloads. Now, if you pull out the CPU utilization of one of the hosts, we see that the utilization is varying in a wide range and has very high variance. We also see that at some points, the utilization is going beyond 100%, resulting in host contention. If you look at the migrations in this scenario, with each spike here indicating the count, we see that load balancer is continuously recommending migrations in such volatile cluster. Now, to handle this host contention and continuous migrations in a volatile cluster, let's look at one of the existing methodologies. Workload prediction in resource management is a very popular existing mechanism. In this mechanism, we try to predict the workload pattern in advance and feed it to the load balancer to make migration decisions. This way, a load balancer can issue migrations proactively to avoid any potential host contention. But for this to work, the VM workload pattern has to be predictable, which is most probably not the case with volatile workloads. And also, the load balancer will still end up performing continuous migrations. As a further improvement to this mechanism, we can have a migration thrash detector that monitors VM migrations in the data center to keep a check on continuous migrations. However, this could potentially result in host contention if we decide to stop moving VMs for a long time. Also, this works better only for short-term volatility because after migrations are stopped for some time and thrash detector sees no migrations happening, it lowers the bar and load balancer continues to start moving VMs again. So in summary, in a highly volatile cluster, a load balancer could still result in host contention and continuous migrations, both of which could highly impact resource availability and application performance. So instead of trying to control or suppress the impact of volatility, a load balancer needs to learn about these volatile workloads and manage them. For that, we propose a new approach called Volatility Balancer that can run along with the load balancer for efficient resource management. The core idea of the Volatility Balancer is simple. Identify volatility as a quantifiable metric and use it to distribute across all the hosts. Let's see this in detail. The first step is to identify volatility. For this, we introduced a new metric called volatility factor, which is a measure of volatility. For VMs, this is computed as a pair of average and standard deviation over past few resource usage samples, and for host, it is sum of its VM volatility factors. Once we compute this cluster volatility factor and compare it against a predefined threshold, it needs to be balanced if it is above the threshold. Since a cluster is always a mix of VMs with different levels of volatility, the idea is to swap a highly volatile VM from one host with a stable or less volatile VM from a different host. But these VMs chosen to swap have to be chosen carefully as we do not want to disturb the existing load balance achieved by a load balancer and undo what it has done, because that will result even in more migrations than what we are trying to stop in the first place. We then continue to repeat these VM swaps until the cluster volatility reaches below the threshold.
You need to accelerate a bit, Priyanka.
Sure. Okay. So finally, the above two steps of identifying and balancing volatility are repeated periodically. To highlight the main points of our approach, Volatility balancer issues VM swaps instead of regular one-way migrations to balance volatility without disturbing the existing load balance. Since it runs periodically, it balances the cluster volatility from time to time and tries to avoid any potential host contention and continuous migrations in a volatile cluster. Finally, this can work with any standard load balancer as a plugin and help in efficient resource management. To look at few results to understand how this approach actually helps, this is a 4-node cluster that we saw in the beginning where utilization is varying continuously. Now, in this scenario with the load balancer, we see that CPU utilization is varying in a wide range and has high variance, and we were also seeing contention at few points. Now, when we ran volatility balancer along with the load balancer, the cluster state looked like this. So here we see that volatility is equally distributed across all the hosts, and now the CPU utilization has very less variance. Due to this, we were also able to avoid host contention in such a highly volatile cluster. If you look at the number of migrations, with load balancer, it recommended more than 70 migrations in a 6-hour run. And when we ran volatility balancer along with the load balancer, we only saw about 25 migrations. This is again because volatility is now equally distributed across all the hosts. This resulted in cluster reaching a steady state and no more migrations after some point in the cluster. So we see that migrations are being reduced by more than half in this scenario. To summarize, when volatility is concentrated on one or only a set of hosts, the load keeps varying on these hosts while other host load remains more or less stable. As a result, load balancer keeps moving VMs in and out of the volatile hosts, resulting in continuous migrations. And with our approach, Volatility Balancer, we propose to identify and balance this volatility across all the hosts to avoid continuous migrations and potential host contention, achieving efficient resource management in a volatile cluster. Thank you.
Wonderful. Any questions for Priyanka and Sai Manohar? So if there are no questions, I have a couple of quick questions for Priyanka and Sai. Question number one, this volatility factor that you spoke about, the metric, isn't that kind of tied down to the kind of applications? So what classes of applications have high volatility, which could reflect in the load on the servers, virtual servers? Hello, are you able to hear me? Hello?
Yeah.
Yeah.
Sorry, could you please repeat the question?
See, you had a volatility metric that you brought in, which helped the load balancer to achieve more stability and less migration, so the performance improves.
Right.
Right?
Right.
So what class of applications would exhibit high volatility in their execution?
We have seen highly volatile workloads in container-based applications because the applications that are run inside containers mostly are lightweight, which can be easily created and distributed and destroyed.
Okay.
So in such scenarios, we were able to see workloads that were exhibiting this volatility a lot.
Okay. Wonderful. Any other question anybody else has? Okay. On that note, we'd like to give a big round of applause to Priyanka and Sai Manohar for this good work. I think there's a lot of opportunity for expanding on this, and I think they should go ahead with the work that you're currently doing. On that note, I'd like to come to the end of this short research papers session.
Sampath has one question.
Okay, Sampath. Oh, yeah. I didn't see that. Sampath?
No, he just now raised.
Okay. Would you please share what is the difference between HA and FT? High availability and FT, or not high availability? HA and FT, that's the question that Sampath has. Priyanka and Sai, would you like to take the question? It's on the chat box on the right-hand side.
Sampath, you can also speak.
Yeah. Okay, more than that,
I think there is a connection issue with
no
Sampath.
problem. I
Yeah.
think we can take it offline, and Sampath can connect with Priyanka and Sai to further have the conversation. All right, thank you. On that note, we'd like to thank everybody, and we'd like to go over to the next session of the student project showcase. Shashi, would you like to end
Yeah.
the session and switch over?
Sure.
Okay, thank you.